last one, the last class that we had, which was really our entryway of talking about automata at all, and start thinking the way that you will want to think about for the rest of the class. So, however, what we did not get to was another example of a recursive definition. And this is kind of important. And I would like to get into it real quick so that we expand our horizons a little bit and understand what we really have been doing when we talked about recursive definitions of languages. Okay, so remember that defining languages and basically formulating the constraints of the strings that we need to impose upon those strings in order to make them a member of a certain language. So there were certain ways, different ways how we could do that. And the two ways that we use so far is natural language, just the English language to describe what the constraints are that we impose upon strings that belong to a certain language, for one. And the other one was to come up with recursive definitions, okay? Recursive definitions. And we looked into two examples. And in these examples, we first had the English description, natural language description of those strings. And the third one here is the other way around. So here you get the recursive definition first, and thank you. And then we come up with the English description, which is probably coming to us as the most natural way of, understanding what a language is all about. So look at this recursive definition and tell me what kind of language do we have? What are the constraints here? So obviously we have an alphabet, right? It's a language over A, B, and C with this recursive definition. So what does it mean? I mean, you can come up with the ins and outs, and in reality, I would recommend you doing that, especially in an exam. So what does the language look like? Is there a name for strings like that? Can anybody come up with a name for strings like that? Yeah. Palindrome. Did you say palindrome? No. Okay. Palindrome. I meant palindrome. Thank you. So who knows what a palindrome is? Right. Madame, I'm Adam is one, for instance. There are way longer ones. Okay. The shorter one is laughing out loud. I mean, the abbreviation of it. Oh, wow. Okay, so is it an odd or an even length palindrome? Odd. Right. Why is that? You always have at least what? You always have a C. Is that a palindrome? Yep. It reads the same way from left to right, then right to left. So, and then do you what? What do you do then? You arrange what around the C? Either A's or B's equally. Okay. And convince yourself that you can have any arrangement of A's and B's before the C's, but they are going to be in reverse order on the other side of the C. Okay, it's easy to see that, I think. Okay, so here you see a certain characteristic that cannot, who is familiar with regular expressions? Regular expressions is something that we are going to see today again. So normally primitive regular expressions do not allow you to do something like that. That condition that if you have a letter on the left-hand side symmetrically, you have to have the same letter on the right-hand side around an axis in the middle. You cannot express that in terms of regular languages. Regular languages are not powerful enough. What I'm saying here, other languages, and I think I mentioned it the last time, another example is a to the I, b to the I, okay. You can use recursive definitions of languages easily to express this as well. Okay, however, the language class is above of what we are going to tackle next, which is regular expressions, regular sets. So we start out small and we add features, tools that become more and more powerful until at the highest level we have Turing machines, okay? Turing machines, which can do anything that can be done by a computer. The very same things that you can do with your computer can be done by a Turing machine. And your computers cannot do anything more than a Turing machine. So that's the highest level, okay? And the point that I want to make is that recursive definitions are a little bit more powerful than we think they are. They already span like two language, they straddle two language classes. Okay, and I think from the very beginning, I gave you, did I give you the bullseye? You should have seen the bullseye, yeah. Okay, so what we just said means that we basically are here. The recursive definitions straddle like two language classes, okay? The most primitive one is here, down here, and we are going to talk about regular expressions today, okay? All right, any questions so far? Any questions so far? All righty, so let's dive right in. As I said, we have like two means of express languages and membership of strings to languages, natural language and recursive definitions. However, recursive definitions, and the book doesn't tell you that, are a little bit too powerful for our purposes. So here we are going to get to know a tool which is on the generating side. So how can we generate strings that belong to a certain language? So, and we will follow up by automata that have the same capability just from the acceptance side. So we will see that both of these tools, regular expressions, regular sets, directly correspond to finite state machines. Okay, so this is kind of a synopsis so that you know what we're looking at. Okay. Alrighty, so languages and set operations. As I said, this is the third tool to express how to generate strings that belong to a certain language. So before we were, this is not quite complete, defining languages using recursion and of course natural language description. What we're going to do now is we're going to making use of what we saw before in the terribly boring math, prerequisite, looking at that stuff, mostly set operations. So now we're going to make use of that, what we like hopefully warmed up in your brains a little bit. So we are going to use set operations to achieve a way to define languages, and possibly a better one. Because let's face it, apart from the fact that our recursive definitions of languages are more powerful than we would wish they are, they're also a little bit hard to understand, hard to manage. So what we're going to see is that using set operations, we have a simpler way of defining strings. So this is not just intellectual vanity. This has very, very concrete applications. Okay, so if you have not yet looked into regular expressions, then you will be able to do regular expressions. And you will also understand that in a compilation process of translating some source code into an executable program, the very first step is actually to determine what the symbols are of your program. And the symbols, similar to what we talked about, remember when we talked about natural language, what are the indivisible smallest symbol that that we are looking at? It was words in a dictionary. It was not single characters. This is a too low level abstraction level, okay? So here in a compilation process, those tools are actually being used in order to decide what the symbols are of your source code. And again, it's not single characters normally. I mean, unless you came up with a looping parameter that you call I, okay? Who is doing that? Who is using I as a looping, the identifier for looping parameter and for loop or while loop? Who is doing that? You are. You are? Yeah. He is smiling and nodding vigorously. Yeah, I'm not gonna tell your name to Dr. Levering because he's gonna shoot you. He is gonna shoot you. And for a reason. But there's tradition also, and I have to admit, I tend to do that as well. I also did not tell Dr. So, do you know what the reason is why we call a looping parameter I? Say it louder. Yeah. So the real reason is I obviously is an integer. And in the old days, I don't know whether it's still the case, but in the old days when you were writing Fortran programs, a certain character range was supposed to be relating to integers. And it started somewhere, I don't know, it may have started with I actually, down to whatever. So when you were using I, it was automatically understood that this is an integer variable. And that's the reason why it came to be such a forceful habit, you know, and it was projected from generation to generation of developers without even knowing, you know, why they did it. Now you know. Anyhow, you know, sometimes you have single symbols and stuff, but however, so you use regular expressions in order to decide what the symbols are in your source code. And then you decide whether, once you have the symbols and the compiler created a symbol table, then those symbols are being looked at what relations they have. You know, do they fulfill the requirements of an if or a for loop or whatever, okay? So when we talk about set operations here and apply them to the definition of languages, that leads to regular sets. So this is a little bit confusing. And sometimes instructors, when you look at classes in the internet about automata theory, they don't really do sometimes a good job of explaining that they go from languages, boom, you know, 0, 100 to regular sets. What the heck? What does it mean? What's the relationship between the two? What is that? So regular sets are really just also languages that represent a certain level of power, a certain language class, the most primitive languages that you can possibly have, okay? Languages that can be expressed in terms of regular expressions, hence the name regular set. And those languages at the same time can be recognized by finite state machines, okay? Finite state automata. So there is a direct one-on-one connection there, and we are going to prove that actually. So the idea is that we, the operations that we defined on strings, in our math review, that we extend those operations to sets of languages. So this is interesting by itself, sets of languages. Okay, operations on sets of languages. So in other words, what we're going to do is from very small languages, sometimes just a character, a symbol, we construct more powerful, more complex languages. So we also go from finite sets to infinitely large languages. Okay. So this may not sink in immediately, but you will see when we talk about examples of such languages and how we describe them, that you will see that we define infinite languages out of finite sets of very small languages, potentially very small languages, okay? And we kind of string them together by using set operations. So what are those set operations? We're here. Here. So the union, we know what unions are. So we can union languages, obviously. And if our language is just a symbol A and then just a symbol B, two languages, finite, very primitive, then we can union them together and have a new language where we have two strings in there, A and B. Or for our purposes, we can say A is in there or B or whatever else is in there. So there's an implicit or here, okay? An or. When we apply unions, unionization, is that a word? I don't know. Two sets of finite languages, okay? So concatenation is the second set operation, and we only have three, so don't be afraid. Okay, concatenation, just concatenating strings. So how do you apply concatenation to actually languages? At the language level, well, here's a precise formulation of that. So the concatenation of two languages is all the strings UV, so those are two languages, okay? X and Y. And they may contain anything, all right? So they may have the empty string only, they may be totally empty, or they may contain a lot of strings. So what we say here is X concatenated Y is actually any string UV constructed by choosing a certain U from X and a certain Y from, a certain V from Y, okay? So this is how we construct the concatenation of two languages. So in principle, we only need those two operations, but we add a third one, and we add that third one for convenience, okay? The third one is gonna be clean star, and this is, it needs a little bit of an explanation before we go there. So by the way, here's an example. We have those two languages, X and Y. So how do we construct the concatenation of the two languages? Well, it's A. If we choose A from X, we can combine it with any one of the others from the second language. So AE, AF, AG, and then we do BE, and so on. So you get the picture, okay? So pretty straightforward. It should just reinforce the understanding of that what you already have. Okay. So let's play with concatenation a little bit more. So what if we just have one language? How do we interpret concatenation? So you see here, theoretically, that means that what if y is equal to x? So in principle, we just have one language, and now we start concatenating that language with itself. So that's the idea here. Concatenate x with itself. So the way how we write that is, if we concatenate the same language with itself n times, we write x to the n. Okay, so n times. By definition, x to the 0 is lambda, the empty string, by definition. You can try to make semantical sense of it. It's up to you. If you don't try to do that, it suffices to say that x to the 0 is the empty string. Boom, there you have it. Okay. So let's assume for a second that x contains the symbols of an alphabet. So when we say, language over the alphabet A and B, let's just assume for a second that the original x contains just the individual symbols of an alphabet, like AB or ABC or 0, 1 or whatever. Okay, so single symbols. So how do we define x of x squared? Obviously, it's all the combinations that you could get, and you end up with a group of strings that have length 2. If you concatenate x another time, you get strings of length 3 and then of length 4 and so on. And when you say that and you keep going doing that for eternity, infinitely, so the n becomes a variable, if you want, that goes towards infinity, and you add up all of these sets, what you get is x star. Okay, so x star basically is adding up, and here you see the union operator, this one here, adding up from x to the 0, you add x to the 1, x to the 2, x to the 3, and so on. Okay, the result is the clean star. So you will wonder, what the heck, what is clean about that star? It looks pretty dirty to me. The thing is that the guy's name was clean. Okay, he was pretty much a contemporary of guys like Turing and Church and all these big names, when they just made up all of this stuff. Okay, so he was one of those big names. And in honor of him, this is still called the clean star, or just a star operator. So obviously this is a thing of convenience. Okay, I mean, could you formulate all of the possible concatenations yourself? Sure, but it would take you for a while, like in forever while. Okay, so when in the former offering of this class, I was asked, we don't really need that. Sure, but you don't want to be busy forever either. Okay, so that star operator has a very good place, and we're going to see where the place is going to be. Okay, so again, for convenience, we may not want to include the empty string. In this case, it's the plus operator. Okay, So we will see it has its place when you play around with regular expressions. Sometimes you just don't want to have the empty string. You want to have applied a rule at least once or more. And then, you know, like you have a bunch of characters, yada, yada, yada. Here you can have a group of characters, and then you see any combinations of that, any number of such characters. Okay, so this should make sense to some of you guys who have already played around with regular expressions. Sometimes you don't want to have this yield nothing. Okay, so in that case, you don't put the star in there, you put the plus in there. That says at least one of those characters or more. Okay. All righty. So convince yourself that the definition that we just had is pretty much consistent with what we said about sigma and sigma star. It's in principle the same thing if sigma is over an alphabet, and usually it is. So when we say sigma, what we mean is the number of symbols, you know, that comprise an alphabet. So this is very consistent with what we saw before, which was, I don't know, in the second or third lecture. Math, wait a minute, did we talk about that the last time? What is language? Yeah, of course. I've written a book. That book has everything that ever got written before. Here it is, all possible strings over an alphabet. Okay, so that was just a prior class. Yeah.
Is there also a sigma plus?
No. Interestingly enough, there's no sigma plus. That's a really good question. I never thought about it. There's no sigma plus. Interesting. I think the reason is that sigma star is understood to be everything that is possible and always includes also the empty string. You know, any language is a subset of that. So if you do not include the empty string in sigma star, you would exclude languages that do indeed contain the empty string. Okay, so I think that is the reason why. All righty, so what? Nope, not quite there yet. So use the above to define languages. So we can make immediate use of that. Okay, we can say, okay, we use these set operators in order to define languages now, and we're going to convince ourselves that this is actually easier to understand and also to write out than, you know, recursive definitions. So what you see in this example here, don't want to stretch it too much, a language over AB, and it contains at least one BB. Okay, so the recursive definition would be that. So you start at least one BB, so you should include it in the base set of strings that are contained in the language, right? Otherwise, you run there's a possibility that you come up with a language that doesn't contain any BBs. So the recursion is if W is in the language, so are these. So why? Question. This seems to be redundant. This seems to be redundant with this. Okay. Why is it not? So let's assume that we scratch out this one here. And we only have those two strings, yeah?
It's because the word is never in the empty string because the base is never empty. So there's always something in the word, so adding something to before it and after it's more necessary. we could get you the same one.
The last part was important that you just said. So the last part, either beginning or end, that was the hint, which is important here. When you start at BB and then any string W, so what you do, remember, you always prepend A's and B's. So, but not all of the strings of that language necessarily need to end up with two B's in the end. Okay? You're excluding those. And I think that's what you said. Yeah. Very good. So similarly, if you exclude, let me just get rid of that. If you exclude the first two, you end up with strings, only with strings that start with BB. And this is also a limitation which leaves out other strings that also belong to the language, right? So in other words, here in this case, you need to have left-hand side as well as right-hand side concatenation. So now comes the interesting thing. We can write the same thing like this. How do you read that? How do you read that? Yeah.
At least one, or any amount of A's or B's, two followed by two B's followed by an amount, or at 0 or more A's or B's.
Exactly. Very good. So any amount of A, B's in any order, this is what that says. This part here, this part. Okay, in any order, because that's how it is. Where am I? Help, where am I?
That's it.
I hate this when it jumps around. I never found out why that is. Okay, so this is obviously a union of two very primitive languages, A and B. So now that union, we start concatenating, okay, infinitely. So that star makes a combination, any combination of A's and B's possible. So that's the reason why we need the star, because you don't want to have an alternative way of formulating that. Okay, actually we don't. You don't want to come up with any combinations and write them out. Okay, so the star is doing that for us automatically. It says any combination of A and B, including nothing. Okay, so our strings may start with BB, and the same is true down here. Any combinations of A and B following ABB, including nothing. So our strings also may be ending in BB. So question, does that exclude strings that have more than one BB? Yes or no? No, no. Here, we may have just one B. We may have two B's in a row. We may have a million B's in a row. All of this is included in this term. Okay, so it's pretty cool, pretty powerful. So now let's get to this. This is a concatenation already. It's a set that has one element. Set equals language. A regular set has one element, one string. That string is BB. Okay. All righty. So, how about the language over the alphabet AB begins with some non-zero multiple of AAA and ends with some non-zero multiple of BB. So convince yourself that this is also relatively primitive. What you say is, okay, I have one element. I can clean plus that Y plus because we need to have at least one AAA. And here, at least one BBB, okay? Or more groups of such. And in between, anything that you can express with A's and B's, including an empty string, okay? So pretty straightforward. You see that this is incredibly easier to use, that this tool is much easier to define structure and also understand what the structure is of a string when you see it. Yeah.
Would that not be the same without the two clean pluses?
What would it be if I leave those out?
You would still always start with an AA and always end with a BBB.
Right.
But then wouldn't there also be any combination of A's and B's between them?
We're talking about elegance. We're talking about elegance. That's a really good one. That's a really good one. Nobody ever asked that question, and it hasn't been discussed in Dury's lectures either. So the question is, does that preclude strings that have AAA? For instance, in the beginning. So the question is, has this here the same expressive power than what we had before? Are we excluding strings that start with A? Well, the way how this expression works, it may very well be AAA on the left-hand side of that string, right? Yeah, what you see here is, it is really the same, it has the same expressive power. Really good, very nice. So does this violate if we only have two A's? And then whatever, and this is the beginning of the string? It doesn't. It's still a multiple of AAA that we start with. Well, here we just, if this is a B, we didn't make it to 2, 2 times AAA, but it's still a valid string. Okay, so very interesting. I should take a note because that's really cool. That's a good question to ask in class. Alrighty. Good. So let me get that back. So we're talking elegance here, and we're talking minimalism. Okay. So this would be a more minimalistic way of expressing the same thing. Okay. Which one is better? Well, the first one makes your intention clearer. Okay. In the first one, you clearly see that you're shooting for multiples of AAA and BBB. In the second one, you don't see that immediately, but it has the same expressive power. So it's pretty cool. Same number of groups at beginning and end. So you guys, a variation. So the variation is the same number of groups in the beginning and end. So how do we express that? Like this. Okay. Is that the regular set? Is that the regular set? We can kind of write it out. But the question is, have you seen that operation that way? Have we defined it in our set operations before? We have not. We have not. Remember, union, concatenation, clean star, plus operator. This is none of that. So it ties into what I said in the beginning in our last class here. So when we talked about this example here, this is not a regular expression, okay? Or a regular language, a regular set, sorry. So I said before that the recursive definition is slightly more powerful than we wanted it to be. So we can express things that are not going to be part of the most primitive language class, which is regular sets, regular languages, okay? This falls in the same category, so it's not allowed, okay? So you may think as well, about it like that. Alrighty, regular sets. So we have been talking about regular sets all the time now for the last half an hour. So let's formalize what we did above, okay? And I said it already, sometimes instructors get into regular sets just cold turkey, and they come from languages, and out of a sudden they talk about regular sets, and you wonder, what the heck? So the bridge is this. Regular languages contain sets of strings that are regular sets. Okay. So the one word regular languages defines the language class that we are talking about. And the other notion here, terminology, piece of terminology is regular sets, which basically says, okay, the strings in a regular language, they represent a set, and we call that set a regular set because it comes from a regular language. And this is a bridge. Now you shouldn't have any confusion, okay? Because in principle, we are talking about the same thing, just looking at that from different angles, okay? All righty, so here comes the definition of regular set. So we have an alphabet, sigma. Sigma comes up here, okay? So and again, we say what the regular set is recursively. So we have a base case. The base case is the empty language and the empty string. And any symbol in the alphabet, okay? Any symbol in the alphabet. And from these building blocks, we can say, okay, if X, Y are regular sets, and we can start out with these regular sets at the base like this, then we can construct a regular set by applying these operators, but only these operators: union, concatenation, and clean star. So by the way, clean star, I didn't mention that before, you just saw it here. The plus star operator, the plus operator can be constructed out of the clean star, really. So the plus is really just for convenience, okay? And this is also true for regular expressions. The thing that I said before, you come up with a range of symbols and you say, okay, at least one of those or more in any order. This is what that means. If you replace this and you really want to have one symbol, you would say that, but this is convenience. Actually convince yourself that that can be replaced by copy, paste, paste. So this is the same thing. Okay, this is the same thing as the other one. It's just convenience, really. Okay. So this is the same thing as this. Here you say by way of the operator that you want to have at least one. And here you say it explicitly. We have one, and then maybe any number afterwards. Okay. Good. What was it that I wanted to express here? What I wanted to express is that not having the plus operator in here is not a limitation. Okay. So again, we construct our regular set out of more primitive regular sets by applying these operators and operations. Okay. So there's a closure property in the definition contained in here. And this comes in the book. It comes out a little bit awkward. And in the book, it tells you, well, you can only construct strings using those rules. Well, I put the rules down there for a reason. Why would I use other rules? I think what they really want to say is, and again, it comes out awkward in the book. What they really want to say is, I think, if you keep applying these rules, all you ever get is also regular sets. This is important. You stay within the language class. This is closure. So the language is closed in that respect. And the way how you say that, regular sets are closed under union, concatenation, and star. So when you apply those operations, you always also get strings that are in a regular set, not something outside of the class. Okay. So this may not be a surprise right now, but we do have in higher level languages, we do have the situation when we do apply concatenation or negation or whatever operation it is, we out of a sudden end up in a string that is not in the same language class anymore. Okay, so just be aware of it. So here we are closed under union, concatenation, and clean star. Regular sets are pretty much closed under pretty much anything. So a language called regular if defined by regular set. All right. So how do you prove that, especially that closure property? Okay. Well, you take a string and you can take it apart, so you can do something in reverse. Is that regular? Is something that we construct some formulation where we only use those operators? Is that going to be regular? Well, we can take apart this construction and show that it is actually indeed constructed out of more primitive pieces. So I do that here for an example. So this example here, and I keep constructing and building up our more complex expression of our regular set by using more primitive building blocks. Okay. And that's what I do here, like the A and the B, as a base case, and then I have a union, and then I apply the star to it, and I have a concatenation here, and I then in the final step, I concatenate the one part, the other part, and the one part again. And all of that stays within the regular languages, regular sets. Okay, so not a big deal. So in principle, we are done. Okay, in principle, we are done. So, but let's formalize that and make it a little bit more convenient, because it's like awkward to write out these curly braces, these curlies and so on, and these little cups that we write for union and so on. So let's dive into regular expression, which is pretty much an almost one-to-one translation of what we have just seen before. Okay. Basically, we create a pattern tool and we create a way how to write it more compactly. Okay. So the definition of regular expressions is similar to regular sets. It's really that the notation is more compact. Okay. All righty. So the base is what we have seen before. Is this, and I don't want to stretch it too much. And then we recursively define regular expressions. And the only thing really that changes it is that we replace the curlies with parentheses. And we use that little cup. And if we write it more compactly, this makes more sense for us as computer science people, that little cup of the union. In the beginning, I said we should think OR, okay? And the OR, the pipe symbol actually expresses that in a more concise way, in a way that we are familiar with, okay? All righty, so nothing new here. To further make it more compact, we can introduce precedence rules so that we only need to write parentheses where we absolutely have to. Okay, so star is being done before concatenation, before union. Okay, those are the binding rules, the precedence rules. So how do we rewrite an expression like that? Well, we can rewrite it like this. And this looks somewhat more friendly. Okay, not very much, but somewhat. Okay, so I give here some more examples, you know, A or B or C. We go from here to here, and yeah, and so on. So it's not really much different. Okay. Okay, so let's apply what we just said. Okay, and go into examples already. So what does that express? At least two B's. What's the minimum string that would be part of that language? BB, exactly, BB, two B's, just two B's. Okay. So okay, how about we, so this was basically just a warm-up. How do we express at least two B? So this would be exactly two B's. Okay, how do we go from exactly two B's to at least two B's? Well, the first B may be preceded by any combination of A's and B's. Then it may be followed by any combination of A's and B's. And then comes the second B, and then again, any combination of A's and B's. So a straightforward way to describe that would be this here. this is not minimalistic, but it makes our intention clear. We want to have exactly 2 B's in our string. But that's the only requirement that we impose. We have the B here, we have the B here. So we can have anything before the first B, anything between the 2 B's, and anything following the second B, okay? Including other B's. We only say at least 2 B's, okay? So the question is that the same when we go for minimalism? Is the second expression the same, has it the same power as the first expression? Look at it. So when I was preparing for that class and I watched Dr. Dury's class, what he had been done in the past, and he came up with this one, I thought, oh, come on, no way. I mean, what I essentially do is I replace this with this, and I replace this with this. That must be restricting the language too much, restricting it unduly. And when you think about it, we're too focused on replacing that one thing with the smaller expression and that other thing, the more general expression, again with the smaller expression. That seems to be too limiting. But actually it's not. If you try to think it in terms of, okay, I would like to come up with strings that are contained in the more complex one, but not in the more simplistic one, you cannot find strings that actually are not contained. Yeah.
Wouldn't that exclude any strings containing as many B's in the beginning?
Well, good question. Thank you for coming up with that example. Wouldn't that exclude strings that come up with any number of B's, starting B's, like 1,000,000 B's? Well, this can be 0. This can be 0. Now you have 2 B's in a row. This can produce any number of B's on the left-hand side, right? So, but thank you. It's a really good exercise in thinking. Okay. So yeah, you can come up with maybe simplifications of that. How about we leave out this part here? Is that the same? Convince yourself it's not, because you're ending at least in a B. Okay. You cannot end in an A. So this step doesn't work. Okay. And of course, this doesn't work either. So yeah, you can convince yourself that those are different languages. And I encourage you, if you feel underwhelmed intellectually on a Sunday afternoon, oh, wait a minute, we had Dr. Ott's class, and I will get into this and think about it. I feel bored. So how about a language over AB with even B's, containing even B's, containing even B's? Okay, so what you can do is you can come up with a string that has exactly 2 B's. This would be that language. Okay, this has exactly 2 B's. There's a glitch in there. Even B's means no B's also. So, but it's a good start. Okay. So how about, usually that's the technique. You have to do something odd or something even. What you do is for even, you provide the exact formulation, and then you kind of multiply it with the star operator. And that way you always are even. Okay. or odd, you go about similarly. You provide one occurrence and then an even occurrence and multiply this, the latter one, okay? The even occurrence. So, so that would be a good one here, okay? It has the empty string and it has 2 B's, it has 4 B's and whatever. Always even B's, except there's a glitch in there. It also contains no B's because it contains the empty string. Yeah? No, you were like,
I was thinking about it, but you pretty much said it.
okay. So can you think of a string that belongs to the language? No B's, but it's not expressed here? Yeah? All A's. Very good. All A's is not expressed here. Okay, very nice. All A's. You have to have damn B's in there when you follow this. Okay, very good. So how about we proceed? And we enforce precedence. So we can have this, we can have this, we can have this 0 times. That certainly has now strings that only contain A's. But we can also not have this part because it's the clean star, okay? So what we have done is we have this plus the group of strings that are only consisting of any number of A's, okay? So we certainly are better off now, and it's correct. But is it also minimalistic or elegant in the sense of being minimalistic? At least even number of B's. So we were here. What can we leave out? Well, we don't really need this one when you think about it. Okay. So now we have something nice, which is also minimalistic. Any number of even B's, including none, also including any string that has any number of A's only, no B's, okay? So with this idea, how about this? Does that work? It does not. Why? You force the strings to start with a B. If you have B's in there, you force it to have a starting symbol of B. So what can you do in order to fix it? Well, one option is, what about this guy? We put it back on here in the beginning. Okay, then we actually do not have any restriction. All righty, convince yourself that this works. Okay, so only a few minutes left. Strings not containing AA. So this is bad. Do we have a not operator? We don't. So the only thing that we can do is express a not by expressing what we can do, not including the things that we don't want to have in. Okay. So not containing AA. So this obviously is too restrictive. We have only one A in here, okay? So how about we go from here to here? This is better, but we only have pairs of A and B. Okay, AB, 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 and so on. So what can we do? And this is also good in the sense that we may start with any number of B's, okay? We do not start out with an A. So, but still, what about A, B, 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 A, B? Or just A, B, 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 A? That doesn't express that. How about we say there needs to be at least one B here? A plus sign, okay? So that leads, sorry about that. That leads to this one here. But this one cannot end in an A. So how do we come up with an expression that ends in an A? Well, we can say, okay, we enforce it. But this by on itself doesn't work either, because now we have to end in an A. So how about we put these two things together? So that leads to this expression. Okay, on the left-hand side, it does the trick. We can start with an A, but we do not end with an A. On the right-hand side, this one here, we also can start with an A, but we also can end with an A. Okay, so obviously that is not very elegant. So how can we simplify that? Well, we can pull the common, like in math, right? We can pull the common part out. If we pull it out here, what are we left with? Nothing, lambda. If we pull this part out here, what are we left with? An A, this here. So those are the two parts that remain. And this is the common part, okay? So you can think of multiplying it in, right? Because really that's what it is. In principle, we concatenate it back in. So we can concatenate it with here, or we can concatenate it with here. Okay. All right, so okay, regular expressions in practice. We have 5 minutes left. What I really give you is just a very, very quick overview. So if you deal with regular expressions in Linux and Unix, you will see extensions, okay? And these extensions are called extended regular expressions. So we have grep, for instance, the global regular expression processor. It's a tool, a command line tool in Unix. You also can use SED for stream editor that has the same capabilities. I just used it the other day to, and I think I mentioned it in class, to remove all of these nasty style tags, style properties out of an HTML file, because BBLearn is producing bunches of those. So anyhow, there are shorthand notations for certain things that we are already familiar with, like character classes. It's called that, character classes. So brackets and any character. This thing here stands for any one of those characters, exactly one. Okay, and then you can augment that and say, okay, many or none of those, or exactly one of those, okay? So I think that syntax, I think it's more straightforward, okay? But you see, it's something, really something that we have done, and in our terms, it would be expressed like that, okay? A or B or C, okay? So complement So I said, with the tools that we have, we do not have negation. So the caret, is it called caret? I think so. Is the complement. So if you put that as the first symbol in a character class, it means not any one of those characters. Okay. So then we have ranges of characters. So what that means here is any one of those character ranges or number ranges. And so on. Why is the E thing? The book is a whole table of different examples of operators and how they are being used. So you see paramount to what we talked about, star and plus. We have also question mark, which is for 0 or 1 occurrence, okay, which is also there for convenience. Anyway, for some reason, the book made a mistake. The plus really means 1 or more and not 0 or more. I don't know why they made that mistake, but I corrected it here. So if you find yourself confronted with a cleaning task of text, you know, that involves pattern matching, this could be a reference to you. Alrighty, you guys, take care. See you next. Oh, okay, next week. No, Thursday. Thursday, sorry. Thursday. Forget what I just said.
Wow,
No snow day.
it's already Thursday.